December 3rd, 2019. I'm Niles Walter.
I'm Marcius, and this is our final project and lab for Physics 101.01 here at KCC with our instructor, Julia Nicholas. Is that right, Julia? I think it's Julia.
Yes.
That's how I've been putting it on all my papers and stuff. And today we'll be working with Newton's 3 laws of motion and using real-world examples to give you our best descriptions and experiments involving Newton's 3 laws of motion. All right, that sounds pretty good.
Let's get started.
All right, so today we're going to be working on the first law of motion. The first law of motion is commonly called the law of inertia. Objects always want to keep doing what they're doing. That is, if they're moving, they want to stay moving. If they're stopped, they'll want to stay stopped. They'll stay stopped or moving until a force acts upon them. So this ball won't move on its own while sitting on the floor. Its inertia keeps it in one spot. But when acted upon by the force from my hand, we'll see the ball move away. The ball would keep rolling, but the friction force from the floor eventually stops it. So here in our second demonstration for Newton's first law of motion, we're doing water in a container. This would be better done outside or in a bathroom. Somebody else's bathroom preferably. This water doesn't want to move either, as you can see. It's being held into its container by gravity. The container is moved side to side quickly, causing it to spill. So when the container is moved, the water sloshes as it tries to stay in the same place.
The second law of motion gives us a formula for determining how an object accelerates when acted on by force. It tells us that the force is a product of the object's mass times the acceleration it experiences. A heavier object will accelerate slower for the same amount of force than a lighter object. However, the force exerted must be in the same direction as the acceleration for the law to be true. This chair is fairly light, so it can accelerate it very fast. This table has a much higher mass than the chair, so it'll accelerate much slower when I push on it with the same force.
Oh, wow.
The formula also works for changes in force with the same mass, such as when you're driving a car.
If we push the gas pedal lightly and apply a small amount of force, the acceleration will be small. However, if we really get into it and apply a large amount of force, acceleration will be much larger.
Ooh, it's moving. All right, the third and final law of motion is the most well-known law. It states that for every action or force, there is an equal and opposite reaction or force. So when two objects interact, they are both exerting forces on one another in the opposite direction. So for my first demonstration here, it's a pretty basic one. Basically, me leaning against this wall without falling over. So you wouldn't think so, but there are actually two forces that are going to be at work here. Okay. When I exert force against the wall with my body, I won't fall through the wall, hopefully. That's because the wall will be exerting an equal and opposite force against me, hopefully. And because the wall is so much heavier, it can exert much more force than I can. And hopefully here in Building 6 on campus, this wall will also. Oh, we got it. The wall is actually exerting more force than I am, and it's holding me up.
For our second demonstration of the third law of motion, we're going to be having two rolling chairs with people sitting in them. When one person pushes off the other chair, they push that chair away, causing them to accelerate. However, the other chair exerts a force back against the person pushing, causing their chair to accelerate in the opposite direction. Whoa! Did you go farther though? I did.
Why is that, do you think, Niles?
You notice that my chair traveled farther than the other.
Huh.
Our
Trying to
masses
say
are,
something there, Niles?
our masses are slightly different, so that the one with less mass travel further with the same amount of force.
Yeah, and thanks for watching our video.